Okay, well, let's get started. Sorry for being in the wrong room, but hopefully we don't run into that issue ever again. Yeah, so let's see, this is lecture 6. We'll just dive into some logistics. So homework 3 will be released sometime this weekend. It's going to be a mixed integer programming based homework. You're going to be solving the kidney exchange problem, which is a real world problem that people face, where you need people to get kidneys, but only certain people's kidneys go with other people's kidneys. So this is a real life problem, and yeah, you're going to build a model that solves that. The other thing to note is that Cindy, our TA, her office hours are going to be changing permanently. She's still figuring out what day and time works best for her, as well as for the course. So once that's figured out, it'll be posted on Ed. Yeah, so 2 weeks ago we talked about linear programming and mixed integer programming. Today is essentially going to be a continuation of that, as there's still a lot to cover. So just as a brief refresher of what linear programming and mixed integer programming are, we're now diving into the space of optimization problems, where we have some sort of function that we're aiming to maximize or minimize. So with linear programming, the function was a linear function, something with coefficients and variables being multiplied together. And, we wanted to either maximize it or minimize it. But the main point was that, of course, there are going to be some sort of constraints on our variables. So we would say, we'll maximize or minimize it subject to some constraints. So, maybe we said x1 has to be positive, or maybe x1 plus x2 cannot exceed 10. So that was a linear program. And then we said, okay, there's also mixed integer programs, which are the same thing as linear programs, except now we have a constraint that some of our variables are integers. So this in its entirety, that's a linear program. But if we added the constraint that x1 is an integer, now the entire thing is a mixed integer program. And with this mixed integer program, we said some or all of the variables could be integers. And then we also talked about how linear programming is polynomial time solvable. So if you remember, we did that. Come on in. Yeah, different room today. If you remember, we did that algorithm where we drew the constraints as lines, and then we had the feasible region, and then we tested all of the corners. That was our algorithm for solving LP. Turns out that was exponential time, but they're also polynomial time algorithms. Mixed integer programming is NP complete, so a much harder problem. And so yeah, we'll talk a lot today about mixed integer programming. That's probably where our focus will be in its entirety. But yeah, any questions regarding logistics or review before we dive into it? Shoot, I forgot to check that. Oh no. I completely forgot. Break threw me off. I'm sorry. Okay, next week. I'm gonna, let me email myself, and I'm gonna set a reminder. Do the Sudoku extra credit thing, and I'll send that to myself. Scheduled for, let's say, next Thursday at 2 p.m. Okay, I won't forget next week. Good. Any other questions? Guess not. So, okay, today's lecture will be a little bit complex in terms of how we go about solving things, but by the end of today, we'll be able to solve some really, really fascinating problems. So for the first part of class, we're going to be dealing with this problem setting. So you are the proud owner of your business called Quackulous, where you specialize in creating novel rubber ducks. Ducks are my favorite animal, so that's why we're doing rubber ducks. And we'll suppose that it costs $10 to produce a single duck. There's also a fixed setup cost of $250 should we choose to produce any ducks. And additionally, we'll have this constraint that we can only create a maximum of 1,000 ducks. And lastly, we're aiming to minimize our cost of production subject to some unknown linear constraints. So that's to say that, like, just upon reading this, you might just say that, okay, to minimize costs, we should just not produce any ducks. But we'll just say that there are some unknown constraints that tell us that we should be solving this problem and like setting up some sort of linear program. Okay, so if this is the setting, it's clearly an optimization problem because we're aiming to minimize cost. So we'll set it up as some sort of linear program or mixed integer program. So I guess the first question is, like, under this setting, what is the objective function? Where objective function is what we're trying to maximize or minimize in terms of what we see here. Like, we're trying to minimize the cost, but what kind of equation is equivalent to cost in this setting? Yeah. Alex. Yeah. 250 plus 10d, where d is the number of ducks you produce. So that is almost correct, because it unfortunately fails when we produce 0 ducks. So n will be the amount of ducks we produce. Should we choose to produce 0 ducks, this is telling us that our cost would be $250, which is not true, because it would be 0. We have that fixed cost only when we choose to produce ducks. Hello. So how do we fix this? How can we change this function slightly to account for the n equals 0 case? Make it piecewise. Exactly. Yeah, that could be our function, that the cost equals 0 when we produce 0 ducks, or it'll be this 250 plus 10n if we produce more than 0 ducks. Great. So that's going to be our cost function right there. Now, the issue is that this is not a mixed integer program, because the cost function that we had, we just said that cost will be equal to 0 if n is greater than or equal to 0, or 250 plus 10n if n is greater than 0. This is not a linear function. I'm just going to back up just for people who came in late to read the context. So this is the problem setting that we're working in. I'll just give like a minute for people to read over that so they can catch up to speed. OK, hopefully that was enough time. But yes, this is a correct formulation of the cost. But it does not produce a mixed integer program, because our objective function is not linear. Mixed integer program, the whole point of it was that our objective function was linear. It looked something like this. Here we have a piecewise function, or like a discontinuous linear function. So how might we fix this issue? Any ideas?
Just ignore the first piece and solve it for 250 plus 10 as a function and just manually check that expression.
Excellent. And how about we take our first idea will be even more naive, but let's just add a constraint of n greater than 0. So that way, if we add that constraint, then we can just write our cost function as this, and it would be linear. Right? That could be a solution. But of course, the issue with that is we ignore the case of n equals 0. If we have a constraint n is greater than 0, our solver will never consider the case n is equal to 0. So that, of course, is a bad idea. But this follow-up idea is like, OK, let's just set n greater than 0 as a constraint, ignore this part, solve the mixed integer program with this as our objective function, and then at the end, we will manually compare it with n equals 0, because that's the only thing that it excluded. And That should work, because we've covered all values of n. So that works, but could we think of any potential issues or like anything that might be displeasurable about this approach of like taking discontinuities and manually checking them?
Maybe like in this case it's simple to see, but if we have multiple pieces and multiple piecewise functions, we have to keep like manually checking those, and that itself could become a problem to see, like, because here you only have one discontinuity and it's a very trivial one.
Yeah, exactly. So like just graphically, our function, if we were to just graph what this looks like out, the intercept is at 250, and then it has some sort of slope, but we have like a hole there. And of course, the procedure works, but like, exactly, we might be in a situation where there are a lot of pointwise discontinuous points. And, going ahead and checking all of those manually, like, the more discontinuities we have, like, the more annoying it becomes. So exactly, yeah, in this case, it's easy to do manually. Other cases may not be.
Even like, okay, if there's pointwise discontinuities, it's annoying, but we can still check them manually. If it's an entire section of the domain that's discontinuous, and that's like there's a different function that follows in that domain, then that becomes even more tricky to me.
Wait 3 minutes, and I'll answer that question. Okay. So we still have to solve the problem of like formulating this as a mixed integer program, because we haven't done that yet. So this is where we're going to turn to one of the most helpful things in the world of modeling. I mentioned it very briefly last lecture. But whenever we have this situation of like two separate things that could occur, or like some decision is either made or not made, in this case, we either decide to produce ducks or we decide not to produce ducks, then it's very helpful to have an indicator. So we'll just introduce this indicator z. We're free to add whatever variables we want because it's our problem. So I'm just going to say z is going to be my variable. It will be 1 if I choose to produce ducks, and 0 if I choose not to produce ducks. Just a variable I chose to include. But with this variable, is it possible to change our objective function or rewrite our objective function so that it's linear and now fully encapsulates the cost over all values of n? How might we do that?
Z times 250 plus 10.
Yeah. Like if we just instead write 250 times z plus 10n, then if we choose to produce ducks, z will be equal to 1, so we add the 250 fixed cost. If we don't choose to produce ducks, then z will be equal to 0, and we don't get that $250 fixed cost. So all we needed was an indicator. So this is our mixed integer program. So that's our objective function, which is great. There are other constraints that are hidden in the problem. Z is going to be either 0 or 1. It's an indicator. We're producing some amount of ducks, either 0 or more. But this constraint here, this first one, is the most important. In the problem, we said you can only create a maximum of 1,000 ducks. So before, that constraint may have looked like n is less than or equal to 1,000. But now we're saying it's going to be less than or equal to 1,000 times z. And this is important, right? Because again, if we choose not to make any ducks, if z is equal to 0, then we have to have n equal to 0. Our solver must set n equal to 0. And the only way we can do that is by specifying the bounds of n in here. So we're saying it's greater than or equal to 0. We must also say it's less than or equal to 0. That's what z does. And if we do choose to make ducks, then it can be anything in between 0 and 1,000. And 1,000 times z allows for that larger interval. So there you go. It's as simple as that, just introducing an indicator and just modifying your constraint and objective function. Questions on how we did that? Yeah.
More like general question. If you have like n greater than equal to 0, n less than equal to 10, and then n greater than equal to, like basically n can be from 0 to 10 inclusive and 20 to 30 inclusive. Suppose those were your like bounds. That should still be okay, right? Like we don't allow strict greater than or less than, but if it's like discontinuous portion, is that still okay?
I'm not sure. I think you might have to just do two separate linear programs.
So then, like, how can we say z belongs to 0 or 1 and still call that a linear? Like,
I mean, z is just a new variable, so we're just going to say like that's.
Like, you're defining z as being 0 or 1, right? So, like, that's also not continuous in the same sense.
Right.
Or does it work because 0 and 1 are consecutive integers, but if you said z is 0 and 2, it doesn't work?
I mean, I suppose you could also say like z belongs to 0, 2. So yeah, maybe just like you could define a set of values, and like we're just telling our solver like this is what z must be somewhere in here, and then we're just letting it figure out what values it could be. So yeah, like for your example, maybe just say n belongs to this set 0 through 10, 20 through 30. Good question. Okay. You know, not the most exciting example, but let's consider a new problem setting. So Coaculus has undergone some improvements where the cost of production has changed. So now we don't have any more setup cost, which is great. But now the price per duck depends on the amount of ducks that we produce. So again, we still have the $1,000 or 1,000 duck constraint. But the first 400 ducks will be $5 a piece. The next 200 ducks will be $2 a piece. And then the next 400 ducks will be $3 a piece. So as an example, if we chose to create 500 ducks, the first 400 will be that $5 a piece. We have 100 left, so we're in like that second segment. So those extra 100 are $2 a piece. You just sort of add it up. And similarly for $900. Setting kind of makes sense, just different costs of ducks depending on how many we produce. So again, we're looking to minimize costs perhaps. So we would define our objective function. Now it's a lot more complex. Let me just write what the prices were. So the first 400 were $5 a piece, and the next 200 were $2 a piece, and then the next 400 were $3 a piece. So if we want a function to describe the cost, we might break it up into how many ducks we produce. If we produce between 0 and 400, then the cost will just be $5 for each of those ducks. If we do between like 401 and 600, then guaranteed the first 400 will be $5, and then whatever's left over will be $2. And then same thing for this last bucket, where if we exceed 600, then the first 400 are at $5, second 200 are at $2, and then whatever's left over is $3. Okay. So this is clearly not a linear function, but you can imagine it has like applications in certain contexts. We're not always going to see linear functions in the real world. We might see something that looks like this. So somehow we are going to model this piecewise linear function as a mixed integer program. Similar to what we did before, where it was kind of piecewise, but now it's like different lines, different segments, which is sort of what you were asking, I think, right? Okay. This ends up being quite complex, but here's what we're going to do. We're going to introduce 3 new variables, delta 1, delta 2, delta 3. And they're going to represent how far into each segment we're in. And so the reason why this is 400 long, by the way, I should mention that the x-axis is the amount of ducks we produce in hundreds, and the y-axis is the cost, also in hundreds. So the reason why delta 1 is 400 long is because the first 400 have the same price. And this is 200 long because the next is just to maintain, like, just to make it simple. So delta is going to tell us how far into a segment we are. So it's going to depend on the amount of ducks we produce, or rather the amount of ducks we produce will tell us what delta should be. So a bit more formally, the amount of ducks we produce is going to be the sum of our deltas. And critically, note the bounds of the delta. So delta 1 will be in between 0 and 400, because that's the size of this chunk. Delta 2 is going to be in between 0 and 200, not between 400 and 600. So that's a critical observation here. It's going to be between 0 and 200, because that's the size of it. And lastly, delta 3 between 0 and 400. Critically, not between 600 and 1,000. So the visual doesn't match up with the axes, but you should just think of like the delta with respect to where it is in its own segment. So currently, all of the deltas are at 0. They're at the start of their segment. So this corresponds to us not producing any ducks. As an example, if we chose to produce 300 ducks, then we would be here on the x-axis. So our delta 1 has pushed to here. So delta 1 will be 300, but delta 2 and delta 3 will be 0 because we haven't reached there yet. If we chose to produce 500 ducks, then we're here on the x-axis. So we must have crawled past the upper limit of delta 1. So delta 1 is at its maximum. Delta 2 goes up to 500, which is where we're at. So delta 2 equals 100. And you can see summing the values together does give us n. And one more example, 800. We crawl past here. Delta 1 reaches its maximum. Delta 2 pushes, reaches its maximum. Delta 3 goes until we hit 800. So those are the values. N equals 800. So, question?
Are those the only constraints?
What do you think?
You'd also need 2 for so if delta 2 is greater than 0, then delta 1 is 100.
Yeah. So like, exactly. Like these are not the only constraints. Because if we just put it like this, then we could have like delta 2 equal to 200, delta 1 equals 0, delta 3 equals 0. So I guess like, maybe a question is like, can we have delta 1 equal to 200 and delta 2 equal to 100? Like, is this ever something that could occur? And the answer should be no, yeah. So a bit more succinctly, delta 2 is only able to move once delta 1 has reached its maximum. And similarly, delta 3 is only able to move once delta 2 has reached its maximum. So yes, these are just our starting constraints. We just have to codify like everything that we've just mentioned. Okay, what is the objective function in terms of these variables?
I guess it's 5 delta 1, just delta 2 plus 3 delta 2.
Exactly. Yep, and that just follows based off of how we've defined our deltas. Okay. So we're in pretty good shape. We have a linear objective function, and we have some constraints, but they're not the full constraints for the reason I mentioned. Because right now, delta 2 is free to be positive no matter what delta 1 is, and that's not good. So we have to sort of take this relationship of the deltas and put that into our constraints. Okay, we just did that. So here's the observations that we made, that delta 2 can only be greater than or equal to 0 if delta 1 is at its maximum. And the same thing for delta 3, contingent on delta 2.
That should be greater than.
Yeah, I mean, yeah, but it could also be like equal to 0, but yeah, it's just the edge case. So again, we're going to introduce indicators because that like tells us when something has occurred or not occurred. Very similar to the previous example of did we produce ducks or did we not produce ducks? So we'll have this indicator, I1, which equals 1 if delta 1 is at its maximum. So I'll try to draw out the example. It looked something like this. So if delta 1 is here, then I1 equals 1. Otherwise, if delta 1 was somewhere in between, then I1 equals 0. And I2 is the similar thing. It equals 1 if delta 2 is at its maximum. So here's the important observation. This is basically exactly what I just said, but in terms of math. If I1 is equal to 0, that means delta 1 is not at its maximum. So it's in between, it could be anything in between 0 and 400. And we'll be very liberal with our use of equality here. It's just the boundary, like forget about it. But if I1 equals 1, then delta 1 has to be equal to 400, or equivalently in between 400 and 400. So originally, on like the previous slide, that was our constraint for delta 1. How do we modify this with our new definition of indicators to properly encapsulate this behavior right here? Like, I think the upper bound shouldn't change because the upper bound will be 400 regardless of what I is. It's just the lower bound is different. It's not always 0. So how can we rewrite it to match this behavior?
Can it be like I1 times some numbers, like if I1 0 then 0 and then 400? Yeah, 400.
Yeah, just rewrite it as 400 times I1 is less than or equal to delta 1, which is less than or equal to 400. Is it clear why that models this behavior? Yeah. Like anytime there's some sort of change of bounds, depending on if something has occurred or not occurred, you probably want to use an indicator, because that's all an indicator is, telling you if something has occurred or not occurred. So there you go, that's that. Let's move to I2. And the observation here is that, like, visually, if delta 2 is at its maximum, then I2 equals 1. If delta 2 is somewhere not at its maximum, then I2 equals 0. And before, our constraint was 0 less than or equal to delta 2, which is less than or equal to 200. So again, I mean, it's very similar to what we did before. How do we fix it? Okay.
You also technically need I1 to be 1 as well, right? Can you say 200 I1 I2 less than equal to delta 2 less than equal to 200?
We'll get to that, yeah, like soon. Just following the pattern that we had before, it would just be like, yeah, exactly. 200 I2 is less than or equal to delta 2, which is less than or equal to 200. However, like you're saying, let me get to it in a minute. So that's that. There is this critical, like, dependency on I2 and I1. Like if we consider the values that I1 could take on and the values that I2 could take on, like, is it possible for I1 and I2 to both be 0? Yeah, if like we're somewhere here. Can I1 be 1 and I2 be 0?
Yeah.
And when does that occur?
When we're at the
When like we're past the point of this first segment somewhere in the middle of the second segment. Can I2 be 1 when I1 is 0? No, because I2 means we have reached this point here, but I1 is saying I1 is 0 means we haven't reached this point here. So that's a contradiction. That can't happen. And then both of them being 1, yes, that's indeed possible. So right now we're just shoving I1 and I2 into places, but we need to incorporate this relationship of like I1 and I2 can only take on certain pairs. And so the way that we'll fix this, it's a little bit tricky to think about, but I'll just show it to you, is as follows. That if I1 is equal to 0, meaning we haven't reached this point here, then delta 2 must be equal to 0 no matter what. Right? What does that say? If I1 is 0, then delta 2 must be equal to 0. So we will upper bound delta 2 by 200 times I. Because if I1 is 0, then this upper bound will go to 0. And then, I2, if it's 0, that only allows for one value of delta 2. If it's 1, then delta 2 can't take on any values. So that's handling that. But then critically, the other side still works. That if I1 is equal to 1, then we allow delta 2 to float freely up to 200. So we're just changing the upper bound of delta 2. Yeah, this is admittedly very, very complex. But it's interesting because we're moving completely away from just normal, boring linear equations. I'll pause if there's any questions right now.
Why don't we do what Ishan said, like 200 I1 and 2?
That allows delta 2 to go up to 200.
Oh, this is one constraint.
Other questions? And we'll do a similar thing for I3 or delta 3, but this happens to be a lot easier. So delta 3 will be constrained between 0 and 400, like before. Except now it only depends on I2. That if I2 is not at its maximum, then this right-hand side must be 0. Otherwise, it can float freely between 0 and 400. And so that is the entire mixed integer program. Our objective function is the cost that we came up with earlier. We have a bunch of these constraints, which all we did was modified the starting constraints, which I conveniently erased, but it was things that looked like that, and just small modifications. With introducing these indicators, it handles all of those dependencies. So now we can solve mixed integer programs that are piecewise linear. And that is much more incredible than you guys are thinking it is right now. Right now it's just like, oh, what are we doing? But it's pretty cool. And my question was what if we just go all the way? What if we just say, my objective function, it's not always going to be linear. It's not always going to be piecewise linear. Sometimes it's just going to be some sort of arbitrary curve. Can we solve problems that look like, problems that look like this, except now our objective function isn't piecewise linear. Now there's quadratic terms in it, or power of 3 terms into it. Is that possible? So the answer to that is it's a long question and a long answer, but there is something called quadratic programming that is like a heavily researched topic. If I remember correctly, like it is sometimes polynomial depending on like the convexity of your function. But the point is like beyond the scope of what we'll cover. But I still say you can pretty much already solve this with what you know. All you need to do is approximate the function. Just split it up into little intervals, draw like a line of best fit, describe it as a piecewise linear function, and you've got a very approximate solution as to what it could be. Like our curve isn't exactly the blue one, but it's pretty darn close. So the solution we get should be pretty darn close to the correct solution. When I first learned this, I was pretty fascinated by it because this is some really powerful stuff. Like we're solving some very, very difficult problems in practice. Yeah. Okay. Yeah.
It's like, if you approximate it, you have to approximate like overall all of the
That's a really good question, right? You know, I'm producing ducks, and like that's a pretty large domain. But in practice, most of the time our variables are going to have some sort of lower bound and upper bound. Like, it's pretty unlikely I'll produce more than 10 to the 15 ducks, right? So that could be an upper bound. So yes, like it depends on both the size of your domain as well as like how large of splits you make. Like if I choose to really divvy this up by size like 1, like n equals 1 as my deltas, then yeah, that adds a lot more complexity. But if I keep it like very large, then it's a little bit less. So yeah, it depends on the domain, depends on the size, but good question. Cool. Okay, questions on any of this before we switch gears? Okay, I'm going to breeze through this because in my opinion, it's pretty boring. But this section is just like, how do you debug integer programs? And the idea is like, okay, you're going to code your constraints, something like this. We looked at this like a few weeks back, where you just put in your constraints, and something breaks. What do you do? And so like, one idea is you just one by one remove your constraints until something works, and then fix the thing that you last removed. Or another idea is do some sort of binary search where you like remove half of your constraints and then go from that. Like, who are we kidding? Like, if I'm coding this, I'm removing my constraints one by one because that just makes more sense to me. But like, if this makes sense to you, by all means, go ahead. And then this is like, okay, if the solution is wrong, but the model says it's feasible, what do you do? And it's just like, okay, you can fix it. Okay, I don't want to talk about that because that's really boring in my opinion. But if you guys are interested in it, you can ask questions on Ed and I'll answer them. But the slides are there. Okay, so we've managed to skirt around the problem on a lot of people's minds, which is how do these mixed integer program solvers actually work? Thus far, we've just said like, how can we construct a mixed integer program? How do we write a mixed integer program? How do we formulate a problem as a mixed integer program? And then it was always like, okay, we'll just shove it into our solver. Now we're going to figure out how do these solvers actually work. So these solvers use a technique called branch and bound. And actually, a lot of chess engines use a variation of branch and bound. Stockfish uses something called alpha beta pruning, which is pretty similar to this. And this is more or less like a technique more than like a mixed integer programming specific algorithm. So like this technique that we'll talk about, this the skeleton can be used for a lot of different things. And for simplicity, Michael, here's the thing, like we'll just assume that our variables are bounded. Like I'm not going to produce more than 10 to the 15 ducks. So in the real world, most things will have some sort of bound to them. OK, so we will get to branch and bound shortly, but we will build our way up to understanding branch and bound. OK, so we'll just assume we're working with a maximization problem. Minimization problems work the same way, but it's just the words we use might be slightly different. So again, we'll visualize like our search space as a tree, as we've done before. So back in SAT world, we had our root, and then you would traverse a branch and make some sort of decision. Maybe set x1 equal to true, and on the other side, x1 would be equal to false. And then you would go down a branch and make a new decision. Maybe x2 equal to true, x2 equal to false. And we had this very big search tree, and we discussed ways of like traversing it naively, and then we added some new like ideas to make the a little bit more sped up. So it's a very similar idea, except now our situation is a little bit more dire. So we're in MIP world. So whereas before our variable was either true or false, now let's say we're dealing with a variable x1, which is in between 0 and 100. Now it's like x1 equals 0, x1 equals 0.0001, and x equals like that? This is mixed integer program. So some of our variables could be integers, not all of them. So if this is not an integer, this is a pretty massive like branching factor right there. And then we would build a larger and larger tree. Seems pretty impractical. So we'll still visualize things as a search tree, except now our decisions may not be just setting a variable equal to something, but instead bounding it in some way. So yeah, like we have this mixed integer programming P, and now our decision will be splitting the domain of a variable. So instead of doing something that looks like this, instead it would look like starting at our root, and either x1 will be less than or equal to 50, or x1 will be greater than or equal to 50. We'll make the decision to split our domain, add this as a new constraint, and then solve the problem recursively. We're just slowly narrowing and narrowing down our things and like checking all the intermediary points. And admittedly, like it's still a very large tree. We're still dealing with like exponential time stuff. But this is a lot easier. It's a lot more tangible. It's a lot easier to understand. Like it's only a branching factor of 2. Thomas, question? Sorry? If it's equal to 50? Okay, like maybe something like that. Yeah, I mean like, okay, we can have inequalities. We might be doing some repeat work depending on where we go, but we'll just accept that because we're dealing with a very hard problem and we don't want to be doing too much bookkeeping. So maybe it's a little bit easier to look at this through the lens of code. So this is saying like, if all of our variables, we've constrained their bounds by splitting it in half and like going back and forth. So if the lower bound and upper bound are the same, then we have assigned values to all of our variables, which means we might be done. So then we check. If there's a violation of a constraint, we'll say no good, infeasible. Otherwise, we will return the objective value because all of our variables are assigned. If not all of our variables are assigned, we'll choose a variable that has lower bound less than upper bound, meaning we can still split it, find its midpoint, and then recurse on x being less than or equal to the midpoint and x being greater than or equal to the midpoint, and take the maximum of the two. Do we see any potential problems with this? For me, the problem is like with splitting our domain in half consistently. Like if we're here, and we're still saying like 0 is less than or equal to x1, which is less than or equal to 50, and we choose to branch again on x1 and split the domain, and then we keep on doing this, if x1 is not an integer variable, when do we stop? Because we can always calculate a midpoint. So that is definitely an issue, and I will not give a solution to it. Yeah. Yeah. Oh, in that case it would work. Yeah, that's a good point. So that is the solution.
No, that means like it just skips points. It's like
No, because we're recursing, like x will still be tested on all parts of its domain because it's bounded below and above by n. So, yeah, good observation. So, yeah, it turns out that this only terminates on integer programs, but maybe that point is wrong. I'll have to think about that. The issue with like this entire tree search that we're doing is that we have to visit everything. Like we have to visit all of our points because at every point we have a different assignment of variables, and we're trying to find the maximum of the objective function. And this is noticeably different from SAT because once we reached a leaf and we found a satisfying assignment, we just stopped the algorithm because it was a decision problem. With an optimization problem, we have to check a lot of different things and see which one is the best. So that adds a lot to the runtime. This is essentially the same thing as brute force. So not ideal. So just as we did with SAT, when we were like, this brute force approach is kind of slow, we added speedups to it. We added inference. We did things like unit propagation. And that helped us make things a little bit faster. So we'll do a very similar thing here. And the idea is that we're going to leverage linear programming. So you might remember this example from last class where like we thought maybe we could solve mixed integer programming by letting it be a linear program. So all of the variables are unconstrained, solving that, and then maybe rounding its variables to rounding the values to hopefully get the correct answer. And we said that doesn't work. Which is true, it doesn't work. But one observation is that the LP solution to a problem is always at least as good as the mixed integer programming solution. So this is to say that like, given a mixed integer program, it's like maximize f of x subject to constraints, and some of our things are like integers. The solution for this problem, like the objective value evaluated on the best solution, will be less than or equal to if we just said maximize f of x subject to the constraints without the integer stuff. Why is that true? Well, I mean, you just sort of like look at the picture right here, right? Like mixed integer programming says our values can only take on certain things, integers. LP says like, okay, they can be integers or they can be a lot better, so we can only improve them.
I guess it is because if you don't have any constraints, then you can always choose the
exactly, yeah. So LP doesn't solve the problem for us, but it is polynomial, and it might give us some assistance. So yeah, here's the way this is going to work. And I'm not going to give a proof of correctness or like much of an explanation of why this works, because it's a little bit like ugly to explain why we're doing things the way we're doing it. We'll just sort of take a leap of faith and say that this should work because it kind of makes sense, and then go from there. So the way we'll fix searching the entire tree, or like at least expedite the process, is take our mixed integer program and sort of like put it through a linear program solver, which exists and runs in polynomial time. And then we'll take the output of it, and we'll look at the integer constraints of the MIP, the mixed integer program. So this is to say that like we'll put it into the linear program. If it outputs a solution where the variables that we said should be integers just happen to be integers in our linear program output, then good, we're done. We don't have to worry about anything, because by coincidence it worked out. Otherwise, we will choose a variable that's supposed to be an integer, but was outputted as a fraction, and now our subproblems will be split based off of that value. So in a way, it's sort of like before, where we were splitting our domain in half. Now it's just saying like, here, take this value v that might be a good idea to look at and split that way. And again, we're just taking a leap of faith and saying, this seems like it might be a good idea. Let's hope it works. And it does kind of work. OK, we'll talk about this very briefly, and then I'll show you the visual example, because that makes the most sense. This is saying that like we can speed up our search by ignoring some of our branches if it yields an objective value that's less than or equal to something that we found. So visually, maybe I solved this subproblem, and the objective value outputs 100. And then I solved this one, and it's like 120. And then this one, maybe it's like, or let's say maybe it's like 98. And this one's like 96. And then I go here, and this is like 95. If we're at like some decision point and we've already found a solution that gives objective 96, this is just saying if we hit a point where it's less than something we've seen before, we can ignore it. Let's just show it visually, and then we can discuss it a little bit more. OK, before we see it visually, this is the idea of the algorithm called a branch and bound. It just combines whatever we've just discussed. It was developed by these two lovely people. There's a backstory to it, but I forgot it and probably don't want to hear it. So here's it in code form. Given a mixed integer program P, we'll put it into our LP solver. If our LP solver says it's infeasible, we're going to return infeasible, because LP encapsulates MIP. If the objective value is less than or equal to the best seen, we'll just return something very, very small. It's a maximization problem. That's sort of what I was getting at. We'll see it in a moment. Otherwise, if LP happens to satisfy all the integer conditions of our mixed integer program, then we'll return that. Otherwise, choose a variable that's supposed to be an integer, but was not assigned as such by our linear program. And then branch. Go test the bound when it's less than or equal to that value, or greater than or equal to the value. And then go as before. So let's just look at this. So this is a problem that we actually saw 2 weeks ago. It's like we were like buying and selling pies, I think. But that was the setup, or something very close to it. So the algorithm says that, OK, this is a mixed integer program because these two are required to be integers. So the first step is we put it into the LP, and it returns these values for x and y. Now we're going to look at this and say x is supposed to be an integer, it's not, and y is supposed to be an integer, so it's not, and it's not. So we'll choose one of these, say x, and we'll branch. On one branch, we'll check it being less than or equal to the floor of it, 2, and the other branch would be x greater than or equal to 3, I guess, the ceiling of it. So now we're just adding that as a constraint. So we're just saying, now look for x less than or equal to 2. Y still has free reign. And with those new constraints, put it into the LP solver again and get us a solution, which looks like this. X happens to be a 2. Y is 3.889. So x is now an integer. Keep in mind, this is not because we're branching on the value of 2, but rather when we added this constraint, our LP solver said x should be 2 to maximize our value. So this is good. Y is not an integer yet. So now we'll branch on y. So we'll add this constraint. Y is less than or equal to 3. So now we're telling our LP solver, look in this white box right here. Give me the best solution, which happens to be at this corner. 2, 3 gives us the solution of 34. This is a solution because both of them are integers. But still, we have to explore our entire search tree, right? It's not just finding a solution, it's finding the best solution. So we backtrack and test y greater than or equal to 4. So it's saying above this red box and to the left of this line here. Give it to LP. What's my solution? This. Y happens to be an integer, hooray. X is not. So we'll again branch on that. And again, give these constraints to the LP. It gives that. Here we would branch on y. We happen to get another solution. Again, we still need to explore everything because we're finding the best possible solution. So check the other way. Give it to the LP. It gives this. So we've explored here. We backtrack up to here. This branch will be x is greater than or equal to 2. What should happen? Arush?
Fail because you have limiting constraints to the left side of the x level.
Yeah, this branch would say x is greater than or equal to 2, but like Arush pointed out, yeah, x also has to be less than or equal to 2. So like our solver would say x must be equal to 2, but yeah, and then it's just like it throws it out. But like, there you go. We would skip over that. Backtrack here, backtrack here, backtrack here. Test the other branch. And we do something similar. However, here we can stop. Because as we add more and more constraints, you can see that as we go down a level, the values are always decreasing. And you can prove it to yourself mathematically, or you can just think, well, if I constrain myself, I'm only going to do worse and worse, and if I had more freedom. So if I go over here and I get 39.66, if I keep searching this, I'm going to get values less and less than that, but I've already found a solution with 40. So I'm done. That's the entire search. Yeah.
Is this just a really good example? Like, it seems like logically, like, it'd be really hard to like end up at like integer values. There's like so many more like non-integer.
Yeah, like,
Than there are integers.
is it a good example? Maybe. But we also asked that with SAT, right? We always had these problems, and then we like did the search, and it's like, oh, it kind of like ended early. Like, is this just a good example? And the answer is like, yes. There will be bad examples where it takes like a lot longer of time. But the whole point of these algorithms we create is that for most cases, it'll work quite well. This one is a lot harder to understand like why we would suddenly get integers. We're just going to accept that it works and be happy about it. OK. other questions on branch and bound? You can also make it iterative if you want. It's the same idea. Maintain a stack and then pop it off. Like, you can look at it at your own time if you'd like. So normally I ask you guys questions when there are these boxes, but I think people are tired, so I'll answer them. So as we're traversing through branch and bound, we are making some decisions as we go along. Just like with SAT solving, we decided which variables we would assign. We talked about like different heuristics you could do of assigning variables different ways. Here, there's a lot of different decisions we're making. So first is like, which subproblem do we visit next? So the approach we did was sort of like a DFS kind of thing, where you just like keep on going down until you hit a leaf, and then you backtrack up and then go down. That's fine. You could also do like a BFS approach. That might work too. It's just like you can do a lot of different things, or you can do like a best first search. And you're also deciding what variable to branch on. And this could be done a number of different ways. Maybe you do the most constrained variable, or based off of the objective function. All of these different things can be done. The point is that a lot of solvers are aware of these decisions and allow users to like sort of choose what they want to do based off of the problem, because truthfully, there is no best answer. Like, you can do whatever you want. It just kind of depends on the problem. Question?
The reason we did the DFS approach is that you could get the leaves pretty quickly, and then you could prune off branches even before you get the leaves since the value is smaller.
Mm-hmm.
So what advantage would the BFS approach like ever have to the DFS approach? Like, any example?
Maybe like some of the leaves are like at a higher level. So like if we go back here, not all of the leaves ended up being at the same level. So just depending on what the tree looks like, it might be a bit quicker to do it that way. I think DFS is better. It just like makes more sense this way, but the answer is just like it's problem dependent. Okay, I'll talk about this very quickly. There are more improvements you can make on mixed integer programming. One idea is introducing cuts. So this is to say, like, if I have a feasible region and, everything in the white space could be a solution to my mixed integer program, but like only some points within it are parts of a linear program, or sorry, the other way around. If everything in the white space is a solution to my linear program, and only these things that have integers are a solution to my mixed integer program, then maybe I can sort of ignore some of my space here, and make the search space a little bit smaller. And that's something called branch and cut algorithm. And it's just like, let me find ways I can cut down my search space and like simplify things a bit. The way you actually find cuts is like beyond the scope of this, but it's just cool to know that this is an improvement that was made. Okay, let's speed through this because okay, we're going to do this extremely quickly. Because I don't know who wants to do it. This is a new problem. It's called the knapsack problem. The idea is you have a bag that can only carry so much, and you have a bunch of items that have value associated with it and a weight. And you want to carry the most valuable stuff and not exceed the maximum weight. So like here, I'd probably want to choose the ring because it's $5,000 and only 1 ounce. And so the question is like, what's the best subset of things you can take home? So there's two versions of the knapsack problem. One is fractional knapsack, where you can take home any fraction of the item. So for example, I could choose like half of the gold bars. It would be 150 ounces and $2,000 if I choose to do that. So this ends up being a polynomial time algorithm. It's pretty straightforward. You just take the ratio of value to weight, sort them in descending order, and then just greedily select the items available to you until you reach capacity. So, I mean, that's cool. The other version is 0-1 knapsack, which says we must either choose the object in its entirety, 1, or we must not. And this ends up being NP complete.
Wait, is that the solution?
Maybe. I don't remember. I can't.
300 gold and 100.
Yeah, you could do like.
Gold in the ring?
Yeah, you can do like the pot of gold, the ring.
No, the gold bars. Oh yeah, pot of gold ring.
I mean, yeah. So it's not the solution; it's just a solution. Yeah. The point is, we can model this as a mixed integer program using indicators. So xi will be an indicator if we choose the thingy or if we don't. We're maximizing the total valuation, subject to the total weight being less than or equal to its capacity. This is one way of solving it. There's also the dynamic programming solution, which runs in n times w time. This is probably covered in 320 or something. It looks polynomial. It's not, because w could be extremely large. And there's also an n log n approximation algorithm, which guarantees
W is the total weight, right?
this is the capacity of the bag.
Yeah. What do you mean by like
So n is the amount of items, w is the weight. Those two are like kind of independent of one another. So like when we say something's polynomial, we would say like polynomial in terms of n. W could be like 2 to the n.
Oh, yeah.
So yeah, like that's that.
Isn't that just a very big constant? Like it's not sitting right.
It's a very large constant, but like it could be written with respect to n, like exponentially large.
But they're like not related, so like why would you do that?
Yeah, they're not related, but like they could be, right? The point is like w very, very large, exponentially large perhaps. There's also an approximation algorithm which guarantees at least 50% of optimal. So that's saying if the correct solution to this, like the optimal solution gave you $7,000, this approximation algorithm will give you $3,500. Yeah, at least that. It's like, well, that's great, but I want $7,000. So the point is like, we can solve it different ways, and like maybe it'll run a little bit quicker for a mixed integer program, just a different formulation. But the real thing is like, you can actually use branch and bound as like a skeleton for solving it, and it's the same idea as mixed integer programming to linear programming. Get the fractional solution, and then branch based off of what